Good morning, everyone. Welcome to the class ECE451 Control Engineering. Today we will keep working on the state description of systems, and we will try to discuss a control problem. We want to find the feedback controller for a system describing matrix form. Okay, this is a ECE. ECE451 Control Engineering, and this is for the class 10th week Wednesday's class. Alright, yeah, we consider system x dot equal to ax plus bu, y equal to cx plus du. Right. So suppose we have a system described by this way. It's a metric form, and now we want feedback. So what is the feedback? So firstly, I give the structure. So we have x dot. X dot, usually when you have x dot, you will consider integral. You use x dot as the input to this integral, and then the output will be x. Alright. Okay, x dot equal to a times x and b plus u, plus b times u. So I need a times x, right, and add it here. Add b plus u, so I need a b here and the u here, right? U times b plus a times x, then the summation of these two, it is x dot, the derivative of x, then goes through the integral. I have x. And what is y? Y will be c times x, so this is c, right? This is x. C times x plus d times u. This is d. Okay, so we have this one, and then we have output y of t, and the input is u of t. Okay, so this is the structure of it. Now we want to add the feedback. We add the feedback. So add the feedback. So feedback, one is from the output to the feedback. The other way is from x to the feedback. So here we first start from here. We use the feedback here, or maybe just start from here is also fine. Okay. This will be x. So add feedback, I use this x times k, and add it to here, and I have r of t. U of t is here. When signal in this part is u of t, and here's r. We use r as input, and this is the feedback. We call this is a full state feedback. As a full state feedback. We use the state variables as a feedback. Okay. So now we still have these two, right? X dot equal to ax plus bu, y equal to cx plus du, but we have something more. This u, now this is u. U will be r, put a negative here, it will be r minus k times x, and yeah, this is u, but u is r minus kx. We have this one. Okay, so this system is different with the original one because we have one more variables, right? We use r. Now r is the input, And if you want to rewrite this in the standard way of the matrix form of a system, you can work like this. U is R minus K, so you just plug in. So you have X dot equal to AX plus BU. U is R minus KX, and Y equal to CX plus DU. U is R minus KX. So you have these two. We have these two. Then we do some simplify. We have X dot equal to, I want the matrix times X, right? This is X, this is also X. So this is A, this is BK. So A minus BK times X plus B times R. This is the first equation. Second equation now is Y equal to CX. And here's a negative K dkx. So C minus dk times X and plus dr. Alright. So we have a new equation. Right? So by added feedback, we can have an equation. Actually, this equation can be described by the new system. This system can be described by this way. Alright. Now we consider, I give a name for this as equation 1, the original one, and this is equation 2. We add a feedback on it. Right? So we can choose K so that 1 had the required pose. Yeah. No matter what kind of pose, you can choose your pose with your demand, right? You can have different pose, and then you can choose K so that the system has those numbers as pose. Yeah, as you wish. All right. Now, how to do it? Suppose actually this is somehow complex, right? We suppose we want determinant of Si minus A minus BK. We want this one had required pose. Yeah. We find the pose by solve this equation. Actually, this is we have S unknown, right? We try to solve it. You can find the S. Do you want those S? Is a required pose. Now, how to do it? We suppose the required pose they are P1, P2 to Pn. I suppose we have n numbers, we want those poses. Then determinant of Si minus A minus BK, this one, it will be equal to S minus P1, S minus P2, S minus P0, Pm, sorry, Pn. Yeah. Okay. Yeah, you want this, right? The other pose, so we can write the whole equation in this way. But now the poles are required, so that means poles are given. Right? Those poles are given. P1 to Pn are given. So we can have S minus P1 until S minus Pn or equal to like S to the n plus A1 S to the n minus 1 plus until an minus 1s plus an. We can suppose this one write it in this way. Okay, I use A1 to AN. Then how to choose K? How to choose K? The problem is how to choose K. If we just look at this, it's hard, but we can use two steps to solve it. First one, suppose the system, I say A, B, C, D, right? Actually, the system determined by these four matrices. They are in the CCF. They are in the form, in the controllable canonical form. Then we have A will equal to, right, three blocks. Here will be 0, here will be unit matrix, and here are some element. This is A. And B, that's one B, right? Why is it here? Yeah. B will be 1, then 0, 0. Right? It should be like this. Then the characteristic equation. So here, I say here, I say it's a negative beta 1, negative beta 2 to negative beta n, where beta i's are coefficients of Si minus A determinant. Yeah, you can calculate what is that one. Si minus A, right? Si minus A equal to, this gives you the denominator of the transfer function, right? This is the denominator of the transfer function. So y over u will be C Si minus A inverse times B plus D. So this is a fraction. This is a fraction. The denominator of the fraction is just the determinant of this part. Determinant of this part. So suppose P, these poles are given. You want these poles. Then you can have this polynomial. You can have this polynomial. Now A itself looks like this. This one, according to the polynomial, will be these are the coefficients, right? So this will be equal to right, it's Sn plus beta 1 s to the n minus 1 plus beta 2 s to the n minus 2 until beta n minus 1s plus b. Right? So A will have the characteristic equation looks like this, but we want the characteristic equation is this one. So the difference between A and the A minus BK. It is just we want to transfer the A at beta to that A's. Beta to that A's. Okay. RC. Okay. Now A minus BK is what? A is this one. Negative beta 1, negative beta 2, negative beta n, right? Three block. This unit, this is 0. Minus B, 1, 0 to 0, and K. K will be, K is here, right? K is here. K times X, you will have a single value to add to U, to subtract to U, right? U is a single value. So actually, K will equal to K1, K2 to Kn. And then K times X will equal to K1x1 plus K2x2 plus until Kn times Xn. Alright, so this is a K. K will be a row vector, looks like this. So here's a K. K1 to Kn. Right, looks like this. Alright, so what is this one? Negative beta 1, negative beta 2 until negative beta n, the first row. And we separate the rest part to be two parts. This column should be 0 for all element, and then this part will be a unit matrix. And the minus, okay, we do multiplication. This matrix times this matrix will equal to first row times first column, that is K1. The first row times second column, that will be K2 until Kn. Yeah. And then 0 times it. So all the rest they are zeros. You got it? Okay. Then you do subtract. You will have the first row minus first row, right? So it's a negative beta 1 minus K1, negative beta 2 minus K2, the negative beta n minus Kn. Here's 1 minus 0, still 1, the unit matrix. This is 0 minus 0, still 0. So we have these. Then the determinant of A minus BK is what? We can compare here. Determinant of this one is this polynomial. Now determinant of these will be a similar thing, just to change the coefficient from beta to beta plus k. So actually this will be Sn plus beta 1 plus k1 times Sn minus 1 plus beta 2 plus k2 and s to the n minus 2 plus until the term here, the term before this will be beta n minus 1 plus kn minus 1 times s plus beta n plus kn. Alright, so we have the determinant should be this one. And we want that k, right? We want to choose that k so that the required poles are these poles, have the required poles. So we want to choose k so that this part will be this one, right? Will be this one. So this one will be this one. Yeah, this one should be this one. Okay, then we need the coefficients are same. So we can have Sn same, doesn't matter. Then A1 should be beta 1 plus K1. So A1 equal to beta 1 plus K1. And A2 equal to beta 2 plus K2. And so on. The last one should be An equal to beta n plus Kn. Okay. So we have these. Alright, now we have K. What are K's? K1 until Kn are equal to A1 minus beta 1, A2 minus beta 2 until An minus beta n. Okay, you get it. So the step you need to work in this way. Yes, here. Right? You want to find the K. You want to find K so that the system 2 has the required poles. You should know what are those poles. So based on those poles, you can calculate, you can find these. And the system itself, before you add the feedback, you have A, right? So based on that A, you have the denominator of the transfer function, this one. Then you pick the coefficients, beta 1 to beta n, and here's A1 to An, alpha 1 to alpha n. Then you subtract them. A is here, determined by those poles. Beta is here, determined by the original matrix A. Then this alphas times minus this beta. Yeah, this alphas minus this beta. Then you get K. So for CCF, you can find K just by this way. Okay. And beta is here. Beta is obtained here, and alpha is obtained here. All right. So we have this. We use this. We have alpha and the beta. Then I subtract them. Then I have K. Okay, this is for the CCF. Now consider x dot equal to ax plus bu and y equal to cx plus du in general. This time it is not necessary to be a CCF, but we can find the P. Let x equal to P times another x, let's say Z, okay, so that the system, this is system 1, right? System 1 can transfer to a CCF, right? We can do that. What is P? P will equal to C times M, where C is B, A times B until A n minus 1B, right? This is C. And M, there will be, here it looks like a unit matrix, but only the lower part triangular it is 0, and this part should be some numbers. These numbers are just those betas, right? You have A, right? You have A, then you have beta. Let's see, the beta 1 to beta n minus 1, where beta comes from this one, from determinant Si minus A equal to 0. This gives us s to the n plus beta 1 s to the n minus 1 plus beta 2 s to the n minus 2 plus until beta n minus 1 times s n plus beta n. Alright, so beta coming from here. Then you can have this C and M. You put them together, you can have P. Then we say AC, which is P inverse A P, BC equal to P inverse B, CC equal to C inverse C just P and ABC. Then D is still D. Alright, we see this one is the CCF. And we still use that alpha. For the required poles P1 to Pn, we have S minus P1, S minus P2, until s minus pn equal to s to the n plus original one use r, right? Use r, not alpha. This is a start. I use the same notation. This is a piece. So this one, yeah, it's alpha. It's ace alpha 1 s to the n minus 1 plus until alpha n minus 1 s plus alpha n. Okay. We have these. Now we can have k. Let kc, I say this is kc, equal to that, k should be a row vector, sorry. K should be a row vector, right this way. K1 to Kn should be A1 minus beta 1, A2 minus beta 2 should be row vector. Just rewrite it again. An minus beta n, right? In this one. K will be this one. So now K will be, now this is Kc, right? This is alpha 1 minus beta 1, alpha 2 minus beta 2, alpha n minus beta n. And we have this. This is Kc. This is Kc. Kc, so that AC minus BC Kc has poles P1 to Pn. Now we have this. Now what is AC? AC is P inverse AP and minus. What is BC? BC is P inverse B. And then this is KC. Okay, we solve this, we can have the poles. Okay, I just write this one. I say this. This has poles P1 to Pn. Right? We have this one. Then we want A, right? We want A. But we want A minus BK has poles P1 to Pn. Now you compare these two. This one, it is just this one times P and P inverse. A minus BK equal to P times P inverse AP minus P inverse BKC. P times it and times another P inverse. Yeah, like this. So this one, you see, these two cancel. This is A minus, this cancel. This is BKC P inverse. So okay, this is P, right? This is K, right? So K equal to KC times P inverse. That's it. This is the final answer. This is the final answer. KC is this, right? KC is this. And the P is as same as those one. That one in the, when we want to try and find the CCF. Okay, let's put this somewhere. It's here. Right? Yes. P is here. Right? P is here. So K is KC times P. P inverse. What is P? Is this one. And what is KC? KC is this one. KC is this one. Okay. Now we can do an example. We still use that one. I think I used it sometimes before, right? Suppose 1, 2, 3, 4. This is a original matrix. I have A, B is 1, 2, C is 1, 1, and D is 1. Suppose like this. Then the system x dot equal to ax plus bu, y equal to cx plus du. We want this. We check the has poles. We want to find the poles. We need to consider si minus a. This one, the determinant. Right. Those poles will be solution of this. Satisfy this one. So this is a determinant of si minus a will be s minus 1, negative 2, negative 3, s minus 4. So this is s minus 1 times s minus 4 minus 6. So it is s squared minus 5s plus 4 minus 6. So it's a minus 2. Right? So we have this is the denominator of the transfer function. Right? Actually, this is unstable one. You try to, you can solve it. You can solve the S1 and 2 have two poles. There will be 2 times a in denominator, 2a. Here will be negative b plus or minus b squared minus 4ac. C is a negative one, so plus. So this is 5 plus or minus 33 over 2. So you see, when this is a positive, this is plus. So 5 plus square root of 33 over 2. That should be a positive pole, right? You have pole in a positive side, so the system unstable. System unstable. System unstable. System. I give a name. I already use 1, right? I write this way. System 1. So 1 is unstable. Okay, now we add feedback. We call this full state feedback. Add full state feedback. Feedback. Full state feedback. We want that u. Now u is just u, right? Now u is some k times x and the r minus. Okay, u equal to r minus k times x. Yeah, look like this. Yeah, I can write as here ax x dot equal to x dot equal to ax plus bu and y equal to cx plus du. I have x and y. Then add feedback. Add feedback. Oh, I need the x. I need the x to add feedback. Now I go back to the not this is correct. Sorry. We use the structure like this. Structure like this. We have 1 over s. I have x dot and x. I need this x as a feedback. Right. And the system itself, x dot will be ax plus b times u. This is u, right? So ax plus bu equal to x dot. And what is y? Y will be cx plus du. Summation, right? So the system looks like this. Now we add the feedback. I put the k here. Like this. Right. We have feedback. Feedback is here. Feedback is here. K will be K1 and K2 now. Right. This is second order. Second order. Okay. The system second order. So K will be look like this. K will look like this. And we want the pole. We want, for example, we want the pole located at we want it stable, right? The original one is unstable. This part is unstable. The original one is unstable. This one is unstable. Unstable. Well, I want K, make it stable, and we suppose we choose P1 and P2. Suppose, okay, the overall system. Let's say this is a T of S. All right. Suppose T of S will have poles. Whatever it is, we suppose the poles is -3 and 3j. All right. -3, 3j. So poles here. Poles here. Actually, if you want, you can also have another pole. Another pole here, right? You can consider it should be symmetrical, but I have that one will be enough. But suppose TS will have this one. Now, how to choose K? Okay, the problem is here. How to choose K? Then, now, Si minus A, the determinant. Put this. The determinant of Si minus A we already calculate. It is this is -5 something, right? Where I put it? It's here. I already have this one. It is S squared minus 5S minus 2. For poles, -3 plus 3j, and the other one will be -3 minus 3j. We have Si minus A, another A, that is C. The canonical form one, right? This should be S minus -3 plus j, and times S minus, okay, here is -3 minus 3j. Right? We have this one. We have this one. This one will be, we multiply them out. S times S, I have S squared. And S times this constant plus S times this constant. So it is S, okay, S times that, it is 3 plus 3j, right? Plus, right? Minus, turn to be plus. Minus to be plus. So this is 3 plus 3j. S times 3 plus 3j. And S times this part. This part is move the minus inside. So plus 3 minus j. Okay. This is the coefficient of S times this and S times this. And the constant term, it is just multiplication of these two. So it's -3 plus j times -3 minus j. Right, that plus j, this minus j. Then this is S squared plus 3 plus 3j. Oh, I missed a 3. Sorry. 3. Right. So these two we add these two, I get 6s, right? 6. This 3j, this is positive, negative, they cancel. And then the constant term is this one times this one. It is plus, okay, it will be -3 times this 2, I get 9. This is -3 minus 3j times -3, so plus 9j, right? -3 times this 2, and then plus 3j times that 2. I have -9j and -9j squared. J squared is -1, so it's a plus 1. Right, I have this one. So this is a S squared plus 6S plus, okay, this cancel, this is 18, just 18. Alright, so this one actually, these are the betas. Remember, formula, we want to find that K. We need Kc. Kc is alpha minus beta, right? Kc is alpha minus beta. Alpha is coming from these poles. Okay, they are coming from poles. So this is alpha, alpha 1, alpha 2. And these are the beta, beta 1, beta 2. Right. Beta. Yeah, beta is this one is beta is obtained from the original equation, original matrix A. Right? We have beta. So these are the beta, and these are alpha. Now we can have Kc. Kc will be is alpha minus beta, right? Alpha minus beta. Alpha minus beta. So Kc equal to those alpha 1 minus beta 1, alpha 2 minus beta 2. And alpha 1, it is 6 minus beta 1 is negative 5. And alpha 2 is 18 minus beta 2 is negative 2. So this is 11 and 20. So we have Kc looks like this. And then what is K? K will be Kc times P inverse. And P oh sorry, too many paper. Which one? I should have, okay, let's start from here. I have A is here, right? I have A is here. A is here. P equal to that C times M, and C will equal to B. B is 1, 2, right? B and AB. B is 1, 2, and A times B. A times B is 1, 2, 1, 2, and have 5. And then 3, 4, 1, 2, I have 3 and 8, this is 11. So this is C. This is C. And M will be 1, 1, 0, and here will be the coming from this one, should be negative 5. Okay, negative 5. Alright, now we can have it. We have K equal to Kc, 1, 1, 20, this is Kc, and the P inverse, we have P. P is C times M inverse. C times M. So 1, 5, 1, 0, I get 1. Right? Then 1, 5, 5, 1, I get 0. And 2, 11, 1, 0, I get 2. And 2, 11, and the negative 5, 1, I have negative 10 and 11. I have positive 1. Negative 10 and positive 11. Okay, this is with the inverse. So the inverse, I need the determinant of this 1 over the determinant. That is 1, right? 1 times 1 minus 2 times 0. Determinant is 1. Determinant is 1. 1, 1, and 20. I keep it. The inverse, this inverse, you need to flip these two elements, but both are 1. And change the sign of these two elements, so negative 2 here. Alright, this result will be 1 is still 1. 11 times 1 minus 40. So 11 minus 40. 11 minus 40 is 29, negative 29. Right? Negative 29. And this is 20. Okay. We have the feedback. We use K for the parameters for the feedback. Then you can verify whether it is good. You can double check, verify. Let me see. want okay, by add that k, we have this, right? And u this one. So the system is x dot equal to ax plus bu, y equal to cx plus du, and u now is r minus kx, right? It's like this one. So this gives us x dot equal to ax plus b times u, but u now is b r minus kx. This equal to a minus bk times x plus br. Okay. Then the poles, determinant of si minus a minus bk equal to 0. You solve this, you can have the pole. Right? And now let's see what are these. A is here. A, B, C, D is here. So A minus BK equal to A is 1, 2, 3, 4, minus B is 1, 2, and K is negative 29 and 20. So this is a 1, 2, 3, 4 minus 1 times negative 29, 1 times 20, 2 times negative 29 should be negative 58, and 2 times 20 I get 40. So this is 12 minus is a plus, 12 plus 29. Oh, not 12, this is 1 and 2. 1 plus 29 is 30. And 2 minus 20 is minus 18. And 3 plus 15, 8, so it's 61. And 4 minus 40 is negative 36. Alright, so we have this matrix, this one. Then what are the poles related with these? I see this is a with the feedback, okay, AK. Then the SI minus AK, take the determinant, there will be determinant of S minus 30, 18, negative 61, S plus 36. Am I good? I think it should be negative 1. Put K. K is okay. I think that maybe I make some mistake somewhere. Let me finish. And this one equal to S minus 30 times S plus 36 and plus 18 times 61. So this is S squared minus 30 plus 36, so plus 6s, and minus, this is a 9, 3 times it is 3, 6 is 18, and 108, 1080, and plus 61, 18, 8, 48, 1 and 6, so it's 1098. 1098. So this is s squared plus 6s. Oh, it's not so large. They cancel 10 cancel, 10 cancel, and 80 cancel. So 18 plus 18. Is this one? Okay, so this one I can write as s plus 3 squared plus 3, right? This is 9 plus 9, plus 9. This one equal to 0, give us s plus 3 squared equal to negative 9. S plus 3 will be square root of, that is 3j, right? Square root of negative 9 is 3j. So you have s equal to negative s, you will have negative s, negative 3, s equal to negative 3 plus or minus 3j. Yeah, as our required, right? We want the system has these two numbers as poles. Now we got it, right? We got it. So this one is good. The K just use that negative 29 and 20 will be good, right? Okay. So this is the method how to assign K, assign the feedback to a system. If you want the pole locating somewhere. And here the calculation, we need several steps. First one, you need to use A. You find these characteristic equation. You have this denominator of the transfer function of the original system, right? And the second part, you need to find that based on the required poles. Took too many paper. I put this somewhere. This one? Not this one. I see. Right. We want to put the poles here. So based on these poles, you have another characteristic polynomial. Okay. So the original system is this part. This one you can find the denominator of the transfer function. Then overall system, you can have another denominator of the transfer function. Okay, so you compare the parameters here and here. Then the required one with the new poles minus the original one. Yeah, the coefficient of S minus coefficient of S. Constant minus this constant. That two numbers, they are the KC. Yeah, this one minus, we get KC. And then K will be KC times P inverse, and the P will be this C times M. C is B and AB. M is this matrix. It is coming from this polynomial. You use these first and second element and put them in here. 1, -5, right? 1, -5. Here's 1, -5. Here's 1, -5. We put it here, and then shift for the next row. Shift to the first row, put in the next row, right? Then you have M. Okay, P will be C times M. Then you can find what is a P inverse. You plug in, then finally you have the K. You can have the K. This process in MATLAB, we have a function. We have a MATLAB function. It is it's an acre something. Acre, yeah. Acre is a person's name. Acre. You need a matrix A. You need a matrix B. You need those poles. Yeah, all the calculation we need these three, right? From A you can find those alphas, right? Those betas, those alphas. I use the notation beta alpha. Yeah, those alphas anyway. Alpha i's, right? And the P, actually you can find those betas. Then you subtract these two, you can have KC. And based on A and B, you can have C and M. Then you have P is C times M, and here X. And finally here will be KC times these. K equal to KC times that P inverse. Alright. Okay, so we have this one. And this process in MATLAB, it is worked just by this function. We can have a look. A bit confused. Yeah. this one, the Acker ABP is a formula like this, and the times let's say is A of A, and this A of A, it is no space. Actually, it's this one. It is this one, but you put no, not this one. It's this one. It is this one. This one, and then put the A here. I should use R. Yeah. So it is 1. 1 now is not 1. Now it should be S to the, so A to the N plus alpha 1 A to the N minus 1 plus alpha 2 A to the N minus 2 plus until alpha N minus 1 times A plus alpha N times unit matrix. So this is similar with these. Right? You have this one. This is a function with variable S. Now you replace S by A. Then you have this one. Then you put it here. You can calculate to get the answer directly from this formula. Alright, I have like A equal to 1, 2, 3, 4. That's A, and B equal to 1 and 2, and C equal to 1 and 1. A, B, C. D is 1. D is 1. Then we have this one. Okay, then we run the ACKER. Here's we need A, we need a B, and we need a P. P will be 2 poles. One is -3 plus 3j, and the other is -3 minus 3 times j. Okay. AB matrix must have same number of rows. Oh, B is wrong. B should be a column. B should be a column. 1 and 2. B should be a column. Then, okay, we have this result, right? And which is our answer? This, our answer is here. Our answer is here, -29 and 20, and this is obtained by my lab. Actually, you can work for more complex case, And here we can also check whether it is satisfy our formula, right? We said that actually it is this one. It is this one formula. If we run this formula, what can we see? We can see it should be 0 and 1, right? Times C inverse C will be B. B is 1 and 2, and A times B. I think I calculate, right? C is here 1, 2, 5, 11. 1 and 2, 1, 5, 1 and 5, then 2 and 11. Right, this is C. And then I need alpha A. Alpha is alpha is, I can find alpha is here. Alpha is 6 and 18. 6 and 18. Alpha is 6 and 18. So times this part will be A squared plus 6 times a plus then 18 times the unit is what? Is ones. I put I here. I don't know what is I. Okay, unit matrix. Can I have these? I can't find. Just ones. I have ones. Oh, just all of them are 1. I don't want that. Okay, I just write it. I equal to 1 and 0, then 0 and 1. It should be a function to give this one. I forgot. Okay, now I run it. Oh, this is so big. I missed something getting wrong. Inverse here. Should be saying inverse. Okay, you got it. Okay, so we can also use this formula. Yeah, you can have it. All right. Okay, this is one topic about the feedback. We want to consider how to determine the gain in the feedback. We use this formula, right? Use this formula. Okay, this is the first thing. Now we consider the second next topic. We have this, right? Consider x dot equal to ax plus bu, y equal to cx plus du. We consider this one. This time we consider we want to add some control part to make the system like the steady state. We want the steady state arrow to be 0. Okay, we want ESS equal to 0. We want this. We need to add some feedback or some controller or something. Right, something like that. So when we add something, finally we want to have this one. We want ESS equal to 0. But firstly, of course. So what is this ESS? What is steady state arrow here? So we say this is a 1. The steady state of system 1. Steady state, that will be when t, you can say is kind of input, kind of initial value. Then when t go to large enough, the value of the output and the state variables, they converge to some fixed numbers. So that is when t go to larger than 1, large enough, then we have x were close to x steady state, y were close to y were close to y steady state. They're constant, the fixed number. Fixed numbers. These two are fixed numbers. Okay. Then they won't change. And of course u is we just use step function. Okay, so u as of t, the step function, unit step, right? Unit step. We use this as input. We want the steadiest arrow. We want to know what is steady arrow, right? We want to find these two. Now how to do it? Okay, we just plug in. We know x dot should be 0 now, right? Because x turned to be a constant, then you take derivative, should be 0. So we have 0 equal to AXSS plus B times USS. Actually this is 1, right? and y, this is also steady state, equal to c xss plus d uss. And uss actually they are 1, right? Because use this one. If you want, you can put some like a u here. Then this will be u, the constant u. All right. Then you can see we have these as equations. We can have this as equations. When x, which one? When this s is given, when s is given, we have unknown y and x. Right? When uss is given, it is 1. Uss is given. So these two unknowns, y and x steady state, they are unknowns. And totally how many unknowns? This is n unknowns. This is 1 unknown. One unknowns and n unknowns, totally n plus 1 unknowns. And how many equations do we have? This will be 1 equation, and this will be n equation, right? N is n by n, and c just 1 by n. Right? C is a row vector, and A is square matrix. So totally we have n plus 1 equations. Okay. We have n plus 1 equations with n plus 1 unknowns. So in generally we can solve it, right? You can solve it. Of course, maybe some special case you cannot, the matrix, the condition is not so good. Maybe you cannot have the solution, but in most cases you can have solution. You solve it, you can have the xs and the yss. Alright. For example, you just use previous one. You can just use this one. Example. I have x star equal to a is 1, 2, 3, 4. X plus bu, b is 1, 2. And y equal to c is 1, 1. X plus du is just 1 times u. And with feedback r, feedback u equal to r minus k. K is negative 29 and 20. The feedback, so the u is this one times x. Okay, so like this one, this one, r is the input, right? R is the input, and y is the output. This one is the input. This is the output. Then we want to know if input is unit step function, then yss equal to what? Okay, you just plug in. We have 0 equal to 1, 2, 3, 4. Here's x ss steady state plus 1, 2 uss. Actually, this is 1, right? Because input. Oh no, this is u. R is 1. Then yss equal to 1 and 1 and 1. Then xss plus uss, and uss equal to r. Okay, r is given, this one. So this is just 1. 1 minus negative 29 and 20 times xss. Okay. So we have these. Then this is okay. We can write it in standard form. It's a 1, 2, 3, 4 xss plus 1, 2 uss equal to 0, and this one is 1 and 1 xss plus uss minus YSS equal to 0. And last one is I still use XSS in the front, so it's a negative 29 and 20 XSS and plus USS equal to 1. So in matrix form there will be 1, 2, 3, 4. U I have 1, 2, no Y, and here's 1, 1, 1, 1, 1, and the negative 1. Okay, and this is a negative 29 and a positive 20, and the U is coefficient 1 and no Y times XSS, then the U SS and YSS equal to 0, 0. This 0 actually is 2 zeros. This is size 2, right? 0, 0. And then third 0, and the last one is 1. We have this. So we have XSS, USS, YSS are equal to the inverse of this matrix. Negative 29, 20, 1, 0. Inverse times 0, 0, 0, 1, which is, okay, I use my lab to find the inverse. It will be a inverse of the matrix. I put something wrong, sorry. Oh, my way to input. The inverse of the matrix and the times a column. The column will be 0, 0, 0, 1. And then the matrix it's 1, 2, 1, 0. First row. Second row 3, 4, 3, 4, 2, 0. Okay, the third row is 1, 1, 1, negative 1, and the last row is negative 29 and 20 and 1, 0. Am I good? 1, 2, 1, 0. 3, 4, 2, 0. 1, 1, 1, negative 1. 29, negative 20. 1, 0. Okay. Alright. So we have X, S, S, U, S, S, Y. So last one is a steady state. Y is here, right? So we can have Y S, S equal to negative 0.0556. This is a negative one. And we can also see what is system. We can define the system like G equal to user system is matrix form is I have A, B, C, D. Oh no, now is with a feedback. So I need this one minus B times K. B times K. Do I have K? No, I don't have K. I need K. K equal to negative 29 and 20. I have K here. Then G will be A minus BK. B will be still B, and D will be still D, and C will be C minus DK. DK. I have this G. Okay, I have this G. Then the step of this G very wrong for a while. You see? The step function, step response, the steady state will be here. This value should be here. Oh, what is value? Can I click it? Yeah, it's negative 0.05 something, right? 0.5 something, and we calculate that. This will be steady state. This will be steady state, and in the graph, it's just this point. When time run, yeah, I can find that point. I think. If I go to E, the cross, yeah, this will be that value, right? 5. Something like here. Should be 556.0556, right? So that is steady state. Steady state of Y is this one, right? Okay, that's all for today. Then next time, let's keep working on this problem. All right. So see you next time. Bye bye.